So when I was a teacher in New York City, I worked at a school that divided the students into two houses. We had House 1 and House 2. And the students were placed before they were sixth graders, before we really knew anything about them. And of course they were just sort of randomly assigned to the two houses, but there were whispers among the students that there was secretly a smart house and a not so smart house. So I was one of the math teachers, and I taught one sixth grade class from House 1 and one sixth grade class from House 2. And to keep it straight in my own mind, I always called the sixth graders from House 1 the blue class, and the sixth graders from House 2 the green class. So every Friday I gave them a 4-minute fluency assessment that tested operations with fractions, whole numbers, decimals, and percents. So what I want to do is I have this data from the two different classes, and I want to test whether or not there is a difference in the academic ability between the two houses. Because the students were assigned to the two houses before we really knew anything about them, they represent random assignment. So I'm going to use the data that I have with each student's average fluency score to compare the difference in means between the two classes using randomization. Math class are going to represent the sample, but there were two other math classes in both houses, so the conclusion is going to give me some information about the population for all sixth graders at this school.
The null hypothesis is that there is no difference in academic ability between House 1 and House 2, and the alternative hypothesis is that there is a difference in academic ability between the two houses. I have 50 jelly beans here to represent the 50 students in my two math classes. The blue jelly beans represent the 24 students in my House 1 class, and the green jelly beans represent the 26 students in my House 2 class. So the students ended up in the blue or green classes just randomly at the beginning of the year, like all the other sixth graders in the school. I'm going to use randomization with these jelly beans to show that each student was equally likely to be in either House 1 or House 2. Since each of these jelly beans represents one student, everywhere the jelly bean goes, they will be connected with the average fluency score for that one particular student. Even though the students ended up in this particular arrangement of a blue class and a green class, it's just as likely that they could have ended up in this arrangement, or this arrangement, or this arrangement. And each of these different arrangements would have resulted in a new class average for House 1 and House 2, and a new difference in means between the two groups. I'm going to take my data and enter it into StatKey as a test for difference in means, so that StatKey can find a whole bunch of different combinations of blue and green jelly beans for me and show me the difference in means for each of those setups. I want the randomization hypothesis test, and I'm going to click on test for difference in means. StatKey already has data entered in here for me, so I need to edit the data and enter the one that I'm working with, which is the blue and the green class. Now we can see the original classes that I actually had. The blue class had an average of 69.183, and the green class had an average of 69.396, which seems pretty close together. And we can notice that the observed statistic is the difference between those two groups, and that is negative 2.1. It's negative because the green class did just a little bit better than the blue class. I want StatKey to show me a different arrangement, so I'm going to put generate one sample with reallocate groups because I want to see what will happen if all the jelly beans are put back into one pile and then distributed between House 1 and House 2. Then I want StatKey to do it over and over again to see all the different arrangements for all the differences in means between the two groups for at least 10,000 samples. Here we're going to use 11,000 samples. And when I do this, you can see that the bell curve is approximately normal and centered at 0, which is my null hypothesis. And it's going to show me all the different ways that I could have had a difference in means for the 11,000 different groups of those jelly beans. Each one of these dots represents one of those groups of jelly beans and the difference in means that you would get if the students had been put into that particular arrangement. Since my hypothesis is wondering whether there is a difference, I'm going to click on two-tail because I don't really care which class did better. I just want to know if there is a difference between the two groups. Now I need to move the cutoff to my observed statistic, which is negative 0.21, and since it's negative, I'm going to click on the left one here to change it. You can see that most of the distribution just turned red, which can tell you a little bit about how likely it is that the two groups would have a difference. The p-value tells me how many arrangements had a difference at that observed statistic or higher out of all of the 11,000 arrangements. It's a little hard to see, but the p-value for the right tail is 0.472, and that's the same for the left tail. So in this case, the p-value is twice that, which is 0.972. This is pretty high, and it means that it's unlikely that the difference that we observed happened by chance. Our data seems to be consistent with what we would expect to see under the null hypothesis, which means that we don't have convincing evidence that there's a difference between the two houses. And as a teacher, that's kind of what I was hoping for. Now I want to check and see what the average difference between the two groups could fall between for all 6th grade students. So I'm going to go back to StatKey, and this time I'm going to go to Bootstrap Confidence Intervals and select CI for difference in means. I'm going to enter my data again, and you can see that we have the same original sample that we had with the hypothesis test. This time, StatKey is going to use my original data and sample with replacement to get a bootstrap sample and use that sample to repeat 10,000 bootstrap statistics. I'm going to click on two-tail, which will tell me the confidence interval at 95%. The confidence interval is from negative 8.446 to 7.833. So that means that the real difference between academic ability on this fluency test between House 1 and House 2 is likely somewhere in that range. It could be that the blue class, which is House 1, can score 8.446 points better than the other class, all the way to the green class, House 2, scoring 7.833 points better. Notice that 0 is in this interval, which supports the decision not to reject the null hypothesis, because it's possible that there is no difference between the two classes. You can also notice that this distribution is centered at our observed statistic, which makes sense because this bootstrap is based off of that data. I am 95% confident that the average difference in academic ability between House 1 and House 2 is between negative 8.446 and 7.833, which means it's plausible that House 1 could do about 8 points better on the assessment, or House 2 could do about 7.8 points better than House 1. In general, it looks like there is no difference in academic ability between the two houses. Now, there may be questions about whether it's appropriate to use a math fluency assessment to generalize academic ability, but for me, this is enough to assure the students that there is no smart house.